Let's talk about Mersenne primes. Mersenne primes are prime numbers that is 1 less than a power of 2. There is something very significant about these Mersenne prime numbers in that we have been able to find only up to 51 of them so far, and here is a listing from Wolfram Alpha that talks about the numbers that we have so far been able to find, and it goes like 3, 7, 31, 127, 8191 and so forth. And as you can see, some of these numbers have been figured out only recently, like in 1983 we found the 30th Mersenne prime, and 51st Mersenne prime was recently found in 2018, and they have not confirmed it yet. They're fairly sure, but not they still have question marks on that. Even now it's a potential Mersenne prime. So, and these numbers can be very, very large. So except for a few that fairly low end, it grows rapidly. There's something very significant about Mersenne primes in that in their relationship between Mersenne primes and perfect numbers, but we'll come to that in a moment. So in this listing that you see here, you can see that some of these are 2 to the power of 607, 2 to the power of 521, and so forth. So let's try to find a few Mersenne primes ourselves. So we wrote a program here, and you can see that it is we are first finding the powers of 2 from 1 to 700, because we know that there are some Mersenne primes around this area up to 607. So we're going to go up to 700th. But the way we are doing it is we are essentially doing a power on 2. However, you can notice that there is an n there. That's very significant. The reason why we made the 2 into an n is that we wanted to treat that n as a large integer. So effectively, this integer can be any size that you want it to be. So 2 to the power of n to 700 is going to be a very large number. And we would not lose accuracy, and that's why we did. And we are going to be operating on the remaining logic here. So here we are saying that find this array of numbers which are 2 to the power of something, and for each of those elements, that is what $$ means, this function is applied. So the function says for the value for each element in this array A, take x, and then x is the number, and first find out, let's try to list the number x and then x minus 1, and because x is a big number, we use the notation 1n to subtract from it so that it will subtract properly, and we will check if that number is a prime number or not. So effectively here we are taking the number itself, which is a big number, and subtracting 1 from it, and that's also a big number. So this less than greater than sign is used to separate the variable name from the n notation. So basically here we are saying the variable x is a big integer, and this way we are able to find out if number that is less than the 2 to the power of x value is a prime or not. If it is, it's going to filter the value, this array that you have here, and it'll take the second. There are going to be 3 elements in each of these cases, so it's going to take, in each case it'll take the third element. So that's the dereferencing for 0, 2. So when you run this, you see that it's going to do all the 2 to the power of 1 to 2 to the power of 700, and it has found these to be the Mersenne primes that you can see. These are very, very large numbers, obviously. So let's see if any of them make sense. If you look at the list from Wolfram, and let's put it next to each other, and you can see that the second column, like 3 is here, 3, 7, 31, then 127, 8191, 13101, 71, 524, 287, 21474, 83647, and so forth. So those are the Mersenne prime numbers, as you can see, and that matches with the listing from Wolfram. And let's compare the relationship between Mersenne primes and perfect numbers. So what are perfect numbers? And perfect numbers are numbers that are effectively you add the proper divisors of that number. And for example, if you take 6, the proper divisors of 6 are 1, 2, and 3. So if you add them up, it returns the number itself. In such cases, it's called a perfect number. So we're going to look for all the perfect numbers in 1 to 10,000 here using this formula. So this equation or this code. So from 1 to 10,000, we are filtering all n's for which the proper divisors of that n, if you add it up, it equals n itself. So when you run this, you get these numbers. So 1, 6, 28, 496, 8128. Now the interesting thing is all Mersenne primes and are related to perfect numbers. And this is something that I believe Euclid and possibly Euler, they proved it, that they are related to each other. So if you know a perfect number, you know a Mersenne prime. So effectively that also means that because Mersenne primes, we have only found like 51 of them yet, we only know about so many perfect numbers too. So how are they related? So let's look at that relationship. For any Mersenne prime, here we have listed 3, 7, 31, 127, which are the Mersenne primes that we found here, 3, 7, 31, 127 and stuff. What we do is we take the Mersenne prime number and we will take the next number to the Mersenne prime number, that is going to be a power of 2, and you multiply these two and you divide it by 2. So in this situation, we are taking each number from here and applying this formula, x multiplied by x plus 1, that is the next number, divided by 2. And this should give us a series of perfect numbers. As you can see here, it is giving 628, 496, 8128 and so forth, which are the perfect numbers that you could see here, 628, 496 and 8128. And so that basically proves the relationship between Mersenne primes and perfect numbers. And the usage that we have made of using big integers and big numbers here to handle extremely large numbers. As you can see that in these calculations, we are going to, so many digits of numbers, and it works pretty nicely. So that's the introduction to Mersenne primes and perfect numbers.